Okay, so next topic is about the uniform rectilinear motions. This one, I emphasize this uniform. What does it mean by uniform? So, uniforms is for the particle in uniform rectilinear motions, the acceleration is 0. This is super important, and this means as a consequence of this acceleration is equal to 0, the velocity is also constant. Okay, so this means this one, acceleration is equal to 0 and velocity is constant. What is the difference from non-uniform motions? Because as you remember last time, you remember the graph here, x, t. Remember the graph last time that you walk home? You walk from here to your house, 32 meters away, and I would say your velocity is like this. No, yes, your velocity. Oops, what happens? Your velocity is like this, and then here comes your accelerations. Let me take a look. Oh, this is my bad. Your velocity look like this. And your acceleration is like this. Okay, means this one acceleration is not equal to 0, so non-uniform. If it is really uniform, the graph should be like this. The acceleration is 0, so the acceleration is 0, and velocity maybe is somewhere here, constant. And for example, your distance will become like this. Slope will as linear equations. Okay, so this is what we call uniform rectilinear motions. Okay, so then please remember, uniform just mean acceleration is 0, and then the following things will, for example, the velocity will become constant automatically. Alright, then if velocity is constant here, then when you integrating the velocity, you will get this formula. And please be careful that this formula is only used for uniform rectilinear motion. If you have accelerations which is not equal to 0, means you cannot use this formula. Okay. Next. So, oh, I forgot one thing. So, what is the example of linear uniform rectilinear motions? Is it a free fall? from parachute? Yes. This is only happens when you are free falling and then you reach the terminal velocity, means your air resistance and gravity is force is canceling each other, so there is no acceleration anymore. For example, why the ants, for example, this is the ants, okay, when they're falling from, for example, 1 kilometers, it's same as falling from, for example, 100 meters. The force or the acceleration or the velocity will be the same. Why? Because you have the air resistance when you are falling, and then if those forces is equivalent, so you reach the terminal velocity, so you are this the highest velocity you can free falling from the sky, then means the accelerations will become 0 at some point. Okay, same as this how to say, same as this example. Then next, what next? For example, if the force is applied to the body constant in a constant directions, and then you also have uniformly acceleration rectilinear motions. For example, you have a guy like this, you push it with F constant, and then accelerations will, I'll say, your force is applied constantly until it reaches the terminal velocity, and then you also when you apply the force and then acceleration will become 0, then this also calls rectilinear uniformly accelerations. Okay, then next, what is the formula for this rectilinear motions? So there will be 3. I think maybe you are familiar with those 3 equation already in maybe in high schools. Okay, but this is just rehearsals for yourself for the next topics, so please be careful that this formula only apply for uniformly accelerations. If the acceleration is not 0, then you cannot use this formula. Then maybe you also interested in several different particles whose motion may be independent or linked together. For example, if you have different people here, Mr. A, maybe change color, Mr. A, still cannot see clearly, Mr. A, Mr. B, Mr. C, Mr. D. There is 4 runners, and they have the different speed, and it's independent in each other, so it's not linked. But here, for A, for B, for C, this is already linked by this cable, by the pulley. This is the pulley, and this velocity of those 3 objects is linked together by these cables. Okay, for example, there will be an example in the futures also, that for example, the displacement of A and compared to displacement of B, the displacement of XB will be 2 times of XA, for example. The reason is there's 2 cables here, and then when you pulling this down, if you imagine pulling this down, this is lift up only a little bit, but here is moving by 2 times of this one. you can try to use your, for example, chopstick and also the rope to confirming this, also possible, right? And next, for motion of several particles, relative motions. So this one, so for relative motions, xb is the distance between here and here, and xa is distance between here and here. And if I say distance b respected to a, means you have to, using distance b here, subtract by this one. So we subtract each other's. Okay? You understand? And in other way around, the distance b is also equal to distance a here multiplied by also summing by the distance b respected to a. Also same as velocities. If, for example, you are here, no, this is the a persons running with the speed of, for example, 10 millimeter per second. He is very slow, I would say. And there is another guy called B, and he running even slower. VB equal to 5 meters per second. So if I say, for example, VB respected to A, this one is equal to VB minus VA, and in the end you get negative 5 meters per second. Okay? And what does it mean? VB respected to A means the A is running and he take a look at B, and it's like when you run faster than B and then you see that the B is seem like has negative velocities. Okay, for example, maybe for more clear example, this VA, he is sitting on the bus. Okay, he is on the bus. The bus is really fast, running with, for example, 1000 meter per second, so to say really fast. And then you are on the bus, and then there you saw the B guys here walking on the walkway very slow. But when you take a look from the bus, you will see that the B is moving backwards because you are running faster. Okay, so let's get to the exercise here. Okay, let's see, what do we have here? Pumps. So we have the ball throwing vertically from 12 meters. So we have here 12 meters, and 12 meter level in the elevator shaft with initial velocity of 18 here, which is 18. At the same instance, the open platform elevator pass 5 meters level moving upward 2 meters per second. Means there is also the elevators here, about here. Okay, this elevator floor, and this is why y elevators ye equal to 5, and then these elevators also move up by ve equal to 2 meters. Right? So, and what did they ask us? Does it mean when and where the ball hit the elevators? And relative velocity of the ball and the elevator at contact. Alright. Okay, then first we separating those two objects, the ball. First I will say ball. We have here ground floor, ball here moving up by VB, I will say V0 B is equal to 18 meters per second, and the height here y V0 is equal to 12 meters, and then we know already that the gravity is or A equal to minus 9.81 meter per second square. And then we have the formulas from previous slide saying that VB or equal to V0 plus AT. Okay, and then from this we can derive that VB equal to 18 minus 9.81 T. Okay, and we also say YB is equal to Y0 plus V0 T plus 1 over 2 AT square. I think you should also remember those formula. And this one is equal to 12 plus 18t plus 1 over 2 minus 9.81 t square. Okay, so this is for the ball. Let's see, this is for the ball and this is for elevator. We know from elevators we are a little bit lower, so here is y elevators 0 is equal to 5 meters, and also v elevator 0 is equal to 2 meters per second. Okay, then we know VE equal to 2 meters per second and YE equal to 5 meters plus 2t. Let's say I get rid of this. Okay. Of course, we have 1 over 2 AT squared, but this one acceleration is 0. And then their questions is when the ball hit the elevators. What does it mean, the ball hit elevators? What does it mean? So, the ball can only hit elevators only when YB equal to YE, right? Same positions means ball and elevators crash. Okay. Then from this formula, we can also say yb minus ye equal to 0 equal to 12 okay, and then you move this will become plus 16t and plus 7 equal to 0, and then here again is quadratics. Equations. Then you can use the formula here again. Right, and then in the end you will get t equal to 3.65 and minus 0.39 second. But then you know already time cannot be negative, so this is in the past. So the answer is t equal to 3.65. Right. So this is the time when it crashed. Okay. And then now you know the times. You already have the formula for the velocity and also the positions. So now it's easy. So you can just plug it in. Ye when time equal to 3.65 second. How much is that? Ye is equal to 5 plus 2 times 3.65, and then is equal to 12.3 meters. This is the time, no, this is the position where it crashed. And last but not least, they asked for, be careful, so it's relative velocity of the ball and the elevators. So relative at the ball and elevators means, is this V, what? B ball and elevators, and this is equal to VB minus VE, and this is equal to 18.981t minus 2. And then this equal to minus 19.81 meters per second. So here is the time when it crashed. Okay, here is the height where it crashed, and here is the relative velocity of the ball and the elevator where it's when it crashed. Right. So then now let's get to the next topics. As I mentioned before, the dependent motions. So the position of particle may depend on the position of one or more the particles. So this one is linked by this stuff, this link by the cable. Okay, and the positions of block B depends on the position of block A, since the rope is constant length. It follows the sum of the length of the segments between the constant. So in conclusions means when you move A down, for example, then the B will move up, but only half of the length. Okay, you may also prove it also, it's fine, right? And here is the relation for the tree of the block also, and here also for velocities you can just take the derivative of those positions, right? No, sorry, so this one is the velocities here, so you will get this velocities relationship, and then in the end you can also get acceleration relationship between those three objects that link together by the cables, right? But if you are interested in this problem, you can also take a look at this samples. So actually it's similar to what we have done, but what we have more additionally for the question is we have the relations between the objects. For example, here you also doing the same stuff. You have to find the acceleration and the times where it's asked, okay, and then in the end you have the relations here also. You have the relation of this movement of the objects, and then in the end you can also find the displacement between those objects. If you are interested in, you can read it through, but from my side there will be no exercise and the exam for these topics. Okay, all right, so here get to the next interesting topics also. Actually, for the positions, accelerations and velocities, it has the many graphical solutions available. Means you have many analyzed method which is more visualized, or is better. All of them are the same to solve the problem, but they maybe show the different stuff that you might need. And here it's just showing you that the given xt curve and vt curve is equal to xt curve slope. So here, if you plot things, if you plotting the slope here, for example, if you can see my pen, you plot the slope for every single point on this positions, and then those slope you will get the number for each slope, and then you plot it here, you will get the velocities. That is the meaning by the velocity curve is equal to positions or displacement over t curve slope, right? And for example, so you can clearly see the slope here, okay, is way more than slope here. Okay, the slope is the inclinations of those line. The slope at this point, I will make it more clear. The slope at this point and this point, this one is way higher than this one. Okay, more slope, less slope, and you can already see it here that the magnitude here on this point is way more than the magnitude here on this point. So this means the point on this graph, okay, is really a slope on each point also from the displacement curve, right? So, and also it's applied for acceleration to the velocity also. The slope on the velocity curve also appeared to be magnitude in the acceleration also. So here is the relation between those accelerations, velocity and the displacement. Okay. And in other way around, the area. So here we start with the accelerations. The area of this curve, this, for example, from T1 to T2, the area over here, okay, I'll make it more clear, is equal to the displacement of the velocity from T1 to T2. So the area here is equal to the height of the, for example, velocity there. Okay. Also same as velocities here, the area here, also the same as the position change of the graph for the displacement. Okay. So also here is some other graphical method that you can also integrating if you would like to find the displacement of this curve. You can also integrating by horizontal approach also, or vertical approach as here. So this is really deep in detail for the calculus. Okay, so next is the curvatures, curvilinear or curvature motions for the position, velocity, and accelerations. For the position of the vectors of the particle at the time t, defined by the vector between O or origins of the fixed reference frame and the position occupied by particles. And consider the particles which occupy position P defined by R at the time t, and P prime defined by R prime at the time t plus delta t. So curvatures means there is a radius here. Okay, this is a radius, and if we have the, of course, when we define the velocity or acceleration or positions, we need also the coordinates, or in this case we using the Cartesian coordinates. And with curvatures, curvature movements or curvilinear movements or motions, we need 3 axes here, or at least 2. Okay, but in this case we wrote it 3, and then when we have this curve, and then the curvilinear motions is just the, for example, I erase also this. So it's just the position on this curve, and then when the time passed by, for example, this is t1, this is t2, when the time t1 and t2, it moved from this point to this point on this curve R. Okay, and the distance is of course between those two, and this is called delta S. Okay, and this delta S is really governed by delta V, no, not delta V, but V equal to delta S and delta T. Okay, then next, it also depends. So you can also use instantaneous velocity vectors of r, and then you also use the difference of the radius here, and also using the difference of the times, or you use instantaneous by scalar, then you use the displacements on this point only. So you can see at this point only the velocity is in these directions. So this is really instantaneous speed. Okay, and this is in these positions, but as you can see in this curve, it's from this point to this point, but this one is used only their point, and then the movements is, if you zoom it in, it seems to be perpendiculars here, so that's why it's written like this, because if you really zoom in, you see the point that it says instantaneous. When you zoom in very much, you get the straight line. Okay, so curvature linear, so we also, in general, the accelerations vectors is not tangents, and the particle path and velocity vectors to the particle path and also velocity vectors. So normally the acceleration here, as you can see, normally, for example, when you are rectilinear motions, you are here, you move by x, and then here is also position of velocity, and here also, for example, the direction for accelerations, for example, it could be in the negative also. But in this case, for the curvilinear, the accelerations is also not supposed to be on the same path as velocities, because you know, when you move to the next point, your velocity is try to bend it here. Okay, as you can see, so means the velocity tend to change its directions. Okay, that's why the acceleration here is really inward here. And last one, this is what we're going to encounter a lot in the futures, because in realities we also have the velocity, acceleration, and displacement in 3 dimensions. And then here is, of course, maybe you're already familiar with this. Remember, we have arm lengths, we have the coordinates, Cartesian coordinates, and here we have ijk as usual. And then this is x, or we can say this is displacement or position. And to find the velocity, you just differentiate these positions, and then you will get directly this one. Okay, and then here's the terms. And for accelerations also, you differentiate the position for 2 times, then you also get something like this, right? Okay, so here is for 2D, and of course in the most problem for for this chapter will be also in 2 dimensions, not really 3 dimensions. Okay. And okay, just read through. So rectangular composition particularly effective when the components acceleration can be integrated independently. For example, this 2, we have 2 axes. We have x and we have y, and you can see that for y we know that when we throwing the objects we will get the A equal to gravitational force. So normally it's 9.81 meters per second. Okay, so this is for y here, and it's really independent than ax, because ax maybe is depend on for example, if you're throwing the ball, it's also depend on how much force, or for example, for ax normally is 0. Okay, we say it's really 0 because you know the gravitational force is affecting only on the y-axis. You know, when you're standing still, you are not moving anywhere, right? You're not moving forward. For example, I've written here, you are standing here. If you do nothing, your acceleration is 0 for the x, right? So there is no movement from your side. Okay, but for example, if you are falling from the sky, then ax is still 0, but ay is also equal to gravitational force. So 9.81 meters per second square. Okay, so that's why in this 2D problems, also please also understanding that y-ax is always equal to 0, ay always equal to minus g, gravitational force, and gravitational accelerations, and az also equal to 0 if we have 3 dimensions, maybe also az is equal to 0. And also with initial conditions, but this is not really, it's depend on you, because normally when you are starting at for example, you're starting at this point, you always set the coordinates directly to this point, means you always start at x0, y0, z0 at it equals to 0. So okay, when you integrating twice, for example, when you integrating those ax and ay or az, you will get velocity like this. So for ax, of course, you will get only vx0, but for vy you will get also the terms of from the gravitational force. And for vz, I said that this is 2D motions, just let it 0. Okay, z also 0 because we are in 2D. And also here also is the displacement and from x and y axis. So in conclusions, I would just erase what is not important. Here is what I highlighted for you. You have to understand why ax is equal to 0, ay is equal to minus g. Just neglect the z-axis. We say, is this really a 2D problem? But if it is 3D problems, so v set will also equal to v set 0. Okay, but this is 2D neglected. And when you integrating acceleration at x, you will get this formula. And when you integrating velocity at x-axis, also you will get this. And this is for y. As I mentioned, you get the gravitational force terms. And here also the same. You will get gravitational force terms. Okay, so this is what you have to understand. All right, then next is the sample pump. So I will let you read it through for 2 minutes and then I will start, or you can pause the video if you would like to need more times. Okay, let's start. Okay, so here, oops, sorry, I always struggling with this. All right, so let's draw the problem. We have this 180 meters per second and we say this is 30 degrees, and then the ball is falling down, of course, by gravitational force, and maybe not really straight, but anyway the height here is 150 meters. Okay, and okay, so then what are they asking? First, with the initial velocity of 180 meters per second, the angle is 30 with horizontals. Neglect the air resistance, that's why it's good. Find a horizontal resistance from the gun to the point where the projectile strikes the ground. So this is where the projectile strikes the ground, and what they would like us to find is the horizontal distance. So from here to here, x equal to what? No, it's a little bit beyond. And b, the greatest elevations above the ground reached by the projectile. So means here also okay, so they are for two things. And right, then let's start solving the problem. So what do we have now? So we given v 0 equal to 180 meters per second, and we have a y equal to minus 9.81 meters per second square. We have y0 equal to 150 meters. We have ax equal to 0 meters per second square. Right? Okay. So first, at the ball or whatever it's shooting, you have this 30 degrees and 180. What you have to do first, same as the problem before for the statics. Of course, you have to decompose these vectors into two axes here. So we will get v x0 and vy0, and we get vx0. So vy0 is equal to v0 sine 30. Okay, and alright, then this is 180 sine 30 degree is equal to 90 meters per sec, and vx0 is equal to v0 cos 30. 180 cos 30 is equal to 155.9 meters per second. Okay, so from this we know already Vy. So let's see, we have Vy equal to Vy0 plus At. This, I think this one you already know from the previous slide, and Vy is equal to 90. Okay, and then you also have y equal to Ey0 t plus 1/2 at squared, and y equal to 90t minus 4.90 t squared. And then we have also last one, Vy squared 0 plus 2ay. So we will get Vy squared equal to 8100 minus 19.62 y. Okay, so I'm just starting to derive all the what we have for the verticals motions. Okay, so for horizontal motions, so we have Vx as we have all it's above already, and we have x equal to Vx0t and is equal to x equal 155.9t. Okay, so what about the horizontal distance? So we say, so if you remember here, we say this is our axis here. So we have y and x. We're starting from 0 on this point, and you know that when it hit the ground is where y is equal to negative 150 meters. So to find horizontal distance, so y equal to 1 minus 150 meters, because when it hit at the negative 150 meters. Okay, then you're substituting to this equation 1 into 1, and then you get 150 equal to 90t and then 4.90t squared, and then here is also the quadratics formulas, right? Okay, so this one you just would like to find the times where the ball is hitting the ground. Okay, that's why you use this formula, and then you get t squared minus 18.37t 30.6 equal to 0. Then when you do what I did before, then we get 19.91 second. Okay, and I think maybe this one you can have a look at the first questions. How can I solve these quadratic equations? And then you know already that this is the time where it hit the ground. So you derived it from, okay, so this one, what does it do, this one? Okay, now you just only standing on the cliff, the ball throwing upwards, so you don't care about the distance in x-axis, there's only y-axis, and then you just find the time. What is the time is have take to falling down, and these times also corresponding to the distance, because you know if the time is more, you will get more distance from traveling in x-axis. So maybe, so to say, I will solve it for you. So to find the distance in x-axis, how long does it take, how to say, how far it have to hit the ground here? You already know the times it took to hit the ground, which is t equal to 19.91. Then you can just use this time, plug into the formula in horizontals here. So I would say equation 2, and then this is into 2, equation 2, then you got x equal to 155.9 times 19.91, and then in the end you get 3,100 meters. Quite long, huh? And then here is what the answers for the first questions. And for the next one, the greatest elevations above the ground reached by the projectile. So, okay, I will just call this A. This is B. What is the height? If I say the ball like this, what is the height? That height is h max, or you can also say x max. That y max. And then how you can find this? You know that already. You will reach the highest peak when which greatest elevations v is equal to 0 meter per second. Okay, just remember this. You will encounter this all the times. It's always the question that what is the maximum height you could reach when you're throwing the ball upwards. It's always where you have the velocity as 0. And then from this, you can use the formulas up there also. Okay, so where we have velocity, and also here we have velocity and we also have distance, means we can use this formula. We can call it 3, and then from 3 we say v equals 0 into equation 3. and then equation T we get 0 equal to 8100 minus 19.62 y. In the end you will get y equal to 8100 over 19.62. Okay, and then you are above the ground by right, let me see, I put the wrong number in the calculations. So you get the height of 410.8 meters. Okay. So, but be careful, yeah. This is what you throw it from here. The height is here 412.8 meters. Okay, because your coordinate start here is at 0, but they ask is the maximum elevation above the ground. So max elevations above the ground is 412.8 plus 150, which is equal to 563 meters. Okay, so this come to an end of these chapters. So if you have still have any questions regarding all the slides from today, you can also send email to me directly. I will try to respond as soon as possible. Okay, so then thank you very much for today and have a good day and stay safe, and also good luck. Bye.